Welcome to my presentation. First, let me thank you for watching this presentation. My name is Badr Athman, and this presentation was supervised by the esteemed Professor Natalia. As you can see, our topic today is vulnerability testing of MQTT brokers. The presentation is structured as follows. I will start presenting by giving a brief introduction of IoT, followed by an overview of the MQTT protocol and some of its brokers. I will then go into security in IoT, then the experimentational framework, and concluding the presentation with the harvested learning outcomes and possible future extensions. First off, I will start with the introduction. The main objective of this research was to develop and evaluate a framework for vulnerability testing of several MQTT brokers using mutation-based packet fuzzing testing. The Internet of Things, or IoT, refers to the billions of physical devices that are now connected to the Internet, all collecting and sharing data. Connecting up all these different objects and adding sensors to them adds a level of digital intelligence to devices. The Internet of Things is making the world around us more smarter, more responsive, merging the digital and physical universes. Moving on to MQTT, I will briefly talk about the protocol. MQTT stands for Message Queuing Telemetry Transport. This protocol is designed as an extremely lightweight publish-subscribe messaging transport. It is ideal for connecting remote devices with a small code footprint and the minimal network bandwidth. MQTT today is used in a wide variety of industries such as automotive, manufacturing, logistics, telecommunication, etc. The main benefits of MQTT are that it is lightweight and efficient, it has bidirectional communication, it provisions for security, scales to millions of things, and is considered to be a reliable message delivery protocol. This is a study conducted by one of my colleagues. In 2017, a Shodan study showed that 395,000 IoT devices use MQTT. In South Korea, it represents 55% of all the MQTT devices used around the world. Since 2019, devices that use MQTT have increased by 610%, and out of 18,536 organizations, 9,766 of them use the MQTT protocol. MQTT is used in industries around us, such as in manufacturing, automotive, and logistics. For example, in the manufacturing industry, Cellular Holdings implement MQTT to monitor power generation from multiple power implants. And in automotive, BMW's car sharing application relies on MQTT for reliable connectivity. And in logistics, Mindsfield, developed by Siemens, allows to connect machines and physical infrastructure to the digital world using MQTT. Now moving next to the brokers. There exists many MQTT brokers, but in this research I obtained a hands-on experience on 3 open source brokers, which I will discuss in the next 3 slides. As shown in the diagram presented, this is how an MQTT broker architecture would look like. Published messages are shown in blue, while the subscribed messages are shown in dashed green. The messages would simply make their way from a publisher through a broker to one or more subscribers using topics. This is the first broker. Eclipse Mosquito is an open source message broker that implements the MQTT protocol. Mosquito is lightweight and is suitable for use on all devices from low-power single-board computers to full servers. I have chosen this broker to do packet fuzz testing, and the main reasons why I chose it are because it's known to be one of the most popular MQTT brokers, it's simple to use, flexible, and has low restrictions. The second broker, which is VerniMQ, it has a high-performance, distributed MQTT message broker. It scales horizontally and vertically on commodity hardware to support a high number of concurrent publishers and consumers while maintaining low latency and fault tolerance. Finally, the last broker used in this research was EMQX. It is an open source IoT MQTT message broker based on Erlang OTP platform. EMQX is designed for massive client access and realizes fast and low latency message routing between massive physical network devices. Moving on to the security aspect. IoT devices these days are susceptible to many attacks. Some of the most common but not limited attacks are the ones displayed on the screen. 2 of these attacks, which are displayed in white, are more relevant to this research since denial of service and vulnerability exploit attacks are usually conducted through malformed packet-based attacks. The goal of this research was to develop a framework for testing the MQTT brokers against potential malformed packet-based attacks. The most common ways to conduct testing that involves malformed packet is by means of packet fuzzing. And what is packet fuzzing? Packet fuzzing detects potential vulnerabilities by feeding unexpected, random but correctly formed and intentionally malformed inputs to the target program and then monitoring its behavior. These attacks can be very harmful to organizations and individuals, so performing packet fuzz testing can come in handy to mitigate this issue. Some of the main benefits of fuzz packet testing are that it helps provide a good overall picture of the quality of the target system and software. Using fuzzing, we can easily gauge the robustness and security risk posture of the system and software under test. Also, fuzzing is known to be a primary technique used by malicious hackers to find software vulnerabilities. So using this type of testing in our security programs would help prevent zero-day exploits from unknown bugs and weakness in our systems. Another benefit is that fuzzing has a low overhead for both cost and time. Once a fuzzer is up and running, it can start looking for bugs on its own, with no human intervention, and can continue to do so for as long as needed. And finally, fuzzing helps uncover bugs that would not have been detected through conventional testing methods nor manual audits. In research theory and practice, there are three types of packet fuzz testing. First is the black box testing, which generates inputs for a target program without knowledge of its internal behavior nor implementation. It may generate input from scratch or rely on static corpus of valid input files to base mutations on. Second, gray box testing. This box uses taint analysis to obtain some information about the protocol, and it focuses on mutating specific input fields through taint data flows. Third is white box testing, and it generates input for a target program while obtaining detailed information about the protocol, source code, specification, etc. The test box chosen for this research was the black box. The reason is that the fuzzer has no information about the source code. Therefore, it was just fuzzing the broker using fuzz control MQTT packets. The main focus of using the black box testing on the Mosquito broker was to determine whether the fuzzed input would cause it to crash or behave abnormally. Now moving on to the experimentational framework. To break down the experimentation, I have used two Linux-based Ubuntu machines. The first machine has a Mosquito broker that's going to be tested and has address sanitizer integrated to it, in addition to Wireshark to sniff the packets. The second machine has F-Secure, which is the MQTT fuzzer, an MQTT generator, and an MQTT subscriber. I also have added an extra MQTT subscriber on my macOS, and the reason of having these two subscribers is to ensure that the broker is transmitting the messages received from the publisher. This experimentation can be extended further by adding more machines as well as subscribing publishing sensors that all connect to the same broker. I will now do a simple experimentation, and it will briefly go over F-Secure, MQTT generator, as well as address sanitizer, when explaining the setup environment and how all these nodes can interconnect. Now moving on to the demonstration, I have two Ubuntu virtual machines. The one on the right hand side has an IP of 192.168.119.9, and the one on the left hand side has an IP of 192.168.119.7. The machine on the right hand side has a Mosquito broker installed on it, as well as Wireshark to sniff all MQTT packets on the local network. The Mosquito broker has been downloaded from the GitHub repository. It has been cloned onto the Ubuntu machine, and the source code has been compiled and built. Using this block of code, we have integrated address sanitizer to detect any memory leaks or memory bugs while testing the broker. This part of the code is how we would turn on Mosquito broker. The -c flag is how we would tell Mosquito broker to point to this configuration file. We have done some adjustments to this file, such as allowing anonymous to be true. This means that anyone sitting on the local network can connect to the broker. Obviously, this is insecure, but we have done this just for testing purposes. To enhance security, we can simply turn this back to false, as well as adding authentication and implementing access control. I will now be turning on the Mosquito broker. It has turned on successfully, and the configuration file has also been loaded successfully. The broker is running on port 1883. Now we would like to check if address sanitizer is turned on, so we would turn on Mosquito once again, and we can see that there has been a leak sanitizer detected memory leaks. Therefore, we know that address sanitizer is working properly. Moving on to the left hand side, we have an MQTT generator in the top terminal. This MQTT generator sends out packets to the host, which is the broker's IP on port 1883 on topic sensors. the MQTT packets are fixed and they keep on transmitting data to the broker until we manually stop it. Moving on below, we have an MQTT fuzzer as shown. This is a simple MQTT fuzzer. It does not try to implement any fancy protocol. Instead, it plays back recorded MQTT control packets. Fuzz cases are generated using Radamsa, and Radamsa is a test case generator for robustness testing. It is typically used to test how well a program can withstand malformed and potentially malicious inputs. Going down to the MQTT fuzzer, we can see that there are flags that we can use to meet our conditions. One of the most important flags is the ratio flag. This basically indicates how many malformed packets we would like to send. The default is 3, so whenever we send out 10 packets, 3 of them will be malformed. We can change this to 10, which means all will be malformed packets, or to 0, which means every packet sent out is going to be a properly formed packet. There's also a delay flag, which means how many packets we would like to send per second. The default is 1 packet per 50 milliseconds. And there's also valid cases. And the valid cases that we are using in this case are those cases we can simply edit, add, or remove. We also have a fuzzer, and the path to the fuzzer is Radamsa by default. I have also implemented subscribers at the top. I have just turned on the first subscriber. This is the IP of the broker onto topic sensors. We can see that there has been a new connection. I will also turn on another subscriber on this side, and I can see that there has been also another new connection. I would like to turn on the MQTT generator. We can see that now this is generating MQTT packets, and we can know that it's working by checking the subscribers as shown. I would also like to turn on Wireshark, and I would like to filter out only the MQTT packets. So these are the MQTT packets on the network. We can see that the MQTT generator is sending packets and publishing them to the sensors topic. Now going on to the MQTT fuzzer below, we have the ratio set to 3, which means we're going to send out 3 malformed packets per 10 packets. We have the delay set to 1000, which means we're going to send 1 packet per second. If we turn this on, we're going to start looking at the right hand side. We have new MQTT packets that are not being sent to the sensors topic. And we also have malformed packets as shown. Now we can do further testing. We can turn off the MQTT generator, and we can turn on the MQTT fuzzer. We can choose the delay to be equal to 50, and we can choose the ratio to be 10, which means all the packets that are being sent are now malformed, and we can check that this is working properly. Moving on to every packet being sent now is a malformed packet. This can help us detect any vulnerabilities in the broker. This can enhance security in the future. So if we turn off the fuzzer again and restart the MQTT sniffer, and I would like to set the ratio equal to 0. And now we can see that the broker is being fuzzed by a lot of MQTT packets in a very short time. The environment that I have just demonstrated has also been built onto the research lab in Lausanne, and the experimentation has been conducted multiple times to ensure that the core of this research is running well and can be used for any additional implementations in the future. We will now look into the harvested learning outcomes and some possible future extensions to this experimentation. After conducting this research, I was able to harvest beneficial learning outcomes, such as how IoT devices transmit data using publish-subscribe architecture, how to install, operate, and troubleshoot Mosquitto, AMQX, and VerniMQ brokers with very limited resources online, how to modify configuration files, specifically to allow the brokers to accept connections from outside the localhost, how to implement virtual sensors, how to write a Python script that connects and generates MQTT packets to the broker, how to integrate address sanitizer when building the source code of the broker, and appreciating its importance when searching for memory bugs. How to utilize F-Secure and generate fuzzed packets using Radamsa. Turning on Mosquitto broker while it is already on would result in a memory leak detected by address sanitizer. I would like to conclude this research by presenting 8 possible scenarios that we can take into consideration if you are willing to extend this experimentation further in the future. These extensions include, but are not limited to, performing packet fuzz testing on VerniMQ and the MQX brokers, place the fuzzer between the broker and the subscriber, sending malformed TLS certificates to the broker, sending an extremely long chain of TLS certificates to the broker, sending a sequence of MQTT packets that would alternately encrypt the header, then the payload, extend the payload length and place MQTT headers inside the new payload, generate sensors that continuously create new topics while packet fuzzing the broker, and finally use smart fuzzing with random values by picking specific fields that we want to test. And that brings us to an end. I'm delighted that I have had this opportunity to present to you. I would like to thank you for your time and your attention.